Hello, everyone. I'm Wei Shengli, a teacher from Jiangsu University, School of Automotive and Traffic Engineering. Due to environmental protection and increasingly stringent national emission regulations, the search for alternative fuels for engines become a hot topic. So today's topic is low zero carbon fuel engine. The content includes 4 parts. Firstly, I will explain why we need to develop low zero carbon fuel engines. Then, I will introduce the fuel physical and chemical properties. Next, their engine application. Finally, there are summary and outlook. First, let's go to background introduction. Since China promised to reach the carbon peaking in 2030 and carbon neutrality in 2060, and the 75th United Nations General Assembly in September 2020, the Paris Agreement signed by major countries and regions in 2016 has controlled the rise of the global temperature and accelerated carbon neutrality policies and actions. As the lead power of the large number of road and non-road mobile machinery and national defense equipment, internal combustion engine (ICE) not only attacked the important mission of energy saving and emission reduction in the near and middle term, but also face great changes and important opportunities on how to achieve carbon neutrality in the future. This table shows worldwide initiatives to achieve carbon neutrality by many countries. At the 26th United Nations Conference of Parties on Climate Change, each country provided information on the target dates of achieved carbon neutrality and the end target year in the future. The internal combustion engine and the efficient and high power density thermal engine for converting chemical energy into mechanical energy still has a large room for energy saving through the combination of the electrified and intelligent technologies. By utilizing low carbon and zero carbon fuels, ICE can still be widely used in larger scale power equipment such as heavy trucks, construction machinery, ships, and aviation, so as to promote the early realization of the carbon peaking and carbon neutrality in China's energy and the transportation field. As shown in the upper left figure, the use of the carbon-neutral fuels and other renewable fuels has become a long-term strategy for solving climate problems in the countries around the world, including Europe, Japan, and the United States. The use of clean alternative fuels such as ammonia and hydrogen has become a research hotspot. As shown in the upper right figure, effective employment of the more energy-efficient advanced technology, electricity generation, and rapid growth of the renewable all play important roles in emission reduction. Emerging technologies and fuels, particularly bioenergy, hydrogen-based and hydrogen fuels, and CCUS, it means carbon dioxide capture, utilization, and storage, will play an additional role, particularly in the sectors where emissions are frequently changed to reduce. This course aims to achieve energy conservation and emission reduction, and explore the application of the various low-carbon, zero-carbon renewable fuels, such as hydrogen, ammonia, methanol, and natural gas in engines. Part 2 is fuel, physical and chemical properties. Hydrogen can be produced from several varieties of the renewable energy source and efficiently obtained through large-scale electrolysis. And after its reaction with oxygen, water is produced. Additionally, hydrogen combustion or electrochemical reaction can be used to generate thermal or electrical energy as power source for vehicles. The loyal heating values of hydrogen is much higher than that of the gasoline and natural gas. Combining fast nominal flame speeds, lean characteristics, and the high spontaneous combustion temperature make hydrogen internal combustion engine have a high thermal efficiency and potential local resistance. This ensures the hydrogen engine have a high indicated thermal efficiency than gasoline engines. This table compared ammonia physical-chemical properties with some of the common additives used for assisting each combustion. They mean alternative fuel of no fossil origin. It is reported that the significantly higher ignition energy was needed to ignition ammonia when compared with fossil fuels, or to the low ammonia flammability. The minimum ignition energy was reduced when incoming ammonia was discarded into the hydrogen to promote the ammonia and air reaction. The combustion rate of the ammonia is very slow, and newly attained ammonia is difficult to ignite. In addition, the gasification of liquid ammonia requires the absorption of the surrounding heat. When technical challenges for the ignition of the ammonia and the stability of the original flame. You can see from this picture. The table 1 lists the properties of the natural gas, gasoline, and the diesel fuels. Typical combustion properties of the natural gas are given in Table 2. A natural gas is an alternative fuel that utilizes the CNG or LNG as an environmentally friendly fuel instead of the fossil fuels. Exhaust emissions from the NG vehicles are much lower compared with the equivalent gasoline-powered vehicles. In addition, less carbon dioxide is produced by combustion of the natural gas than by combustion of the both diesel fuel and gasoline, which makes natural gas engines fairer in terms of the greenhouse effect. Methanol is a potential clean fuel with advantages of low pollution emissions. Compared to current fossil fuels, methanol has special properties such as the high octane number, heat of the vaporization, and luminous flame speed. These characteristics make it even more attractive for using in spark ignition engines. The high nominal flame speed increases the combustion rate and contributes to improve the ignition stability and thermal efficiency. However, the disadvantage of the spark ignition engines is low energy conversion efficiency, especially for heavy-duty engines with large cylinder bores. Yes, each clean alternative fuel has its own pros or cons. Ammonia can be decomposed to produce hydrogen. Hydrogen can be produced from natural gas by reforming it. Methanol and the methanol can be chemically converted into each other, and the deficiency of the ammonia in the combustion process can be made up by hydrogen, natural gas, methanol, and other active fuels. Okay, next, let us explore the application of the clean fuels in engines. In this part, I will choose 4 renewable low-zero carbon fuels: hydrogen, ammonia, natural gas, and methanol respectively. There are also other new fuel or methods to reduction carbon emissions. Firstly, let's go to hydrogen engine. At present, the use of hydrogen energy in the vehicle industry mainly includes fuel cell and internal combustion engine. Hydrogen fuel cells have a disadvantage in terms of their cost and server life. And the price of the fuel cell vehicle are still much higher than that of the traditional vehicle. Compared with the fuel cells, hydrogen internal combustion engine can take advantages of the mature industry chair and existing technology. Moreover, the purity of the hydrogen is not strictly required. So, hydrogen is an ideal alternative fuel for internal combustion engine. The video shows hydrogen engine.
And welcome. In this video, we're going to talk about the work Toyota is doing on developing hydrogen combustion engines. So the idea is, what if instead of making a whole bunch of new electric cars, we instead took the combustion cars that we already have and converted them to hydrogen-based fuels. And so instead of using a carbon-based fuel, which has carbon emissions, you would have a hydrogen-based fuel, which just has water as its emissions. So you would eliminate those carbon emissions. Now, that sounds like it would make a lot of automotive enthusiasts pretty happy. So what Toyota did is they created a Corolla Sport that was powered by a hydrogen combustion engine, and they entered it into a 24-hour endurance race. And so this is powered by a 1.6-liter turbocharged inline 3-cylinder that comes from the GR Yaris, and then it's been converted over to hydrogen. Now, it's not nearly as simple as saying it's been converted over to run on hydrogen. It's quite a process. In fact, back in 2016, they were still using a 50-50 mix of gasoline and hydrogen because it's very difficult to get it to run on hydrogen alone. But here we are 5 years later, and they have a functional hydrogen combustion engine. So this engine operates much like a typical gasoline engine. It has 4 strokes: intake, compression, power, exhaust. It has direct injection for the hydrogen fuel, and it is spark ignited. So in comes oxygen, you spray in hydrogen, and then your emissions are water. So how did they do in that 24-hour race? Well, the results are less than ideal, but I think keep in mind, it's proof of concept vehicle really that's going out there. So in the 24-hour race, they were able to travel 1,634 kilometers, about 1,000 miles in 24 hours. So not super far. 12 total hours of driving, 4 total hours of refueling. They had to refuel 35 times, which gives them an average refueling speed of about 7 minutes. So 7 minutes is a decent amount of time to refuel, though compared to, of course, an electric car, significantly quicker to refuel. And then 8 hours of time spent repairing the vehicle from things that had broken and doing safety checks to make sure it was safe running around out there. These hydrogen tanks are storing that hydrogen, compressed hydrogen, at about 10,000 psi, 700 bar. Now, we need and welcome. In this video,
On January 8, 2022, a heavy-duty commercial vehicle directly injection hydrogen engine, independently designed and developed by FAW CO Ltd, was successfully ignitioned and ran stably. The hydrogen engine is a 13-liter heavy-duty engine with a running power of over 500 horsepower. The strongest power in its displacement class, and an indicated thermal efficiency of over 55%. This picture shows a Cummins hydrogen internal combustion engine. The hydrogen storage tanks are made of the carbon fiber and are lightweight and very robust. The larger capability of the hydrogen storage system, combined with the efficient direct injection linear technology, provides the truck with the Cummins engine with a potential range of up to about 500 kilometers. And then I will talk about ammonia engine. Although hydrogen is an attractive carbon-free energy source, its storage is difficult and more expensive due to the high compressor pressure of about 350 to 700 bar needed to attain competitive in energy density. As shown, ammonia, on the other hand, exhibits higher energy density than hydrogen with a substantially low pressure of about 10 bar. This video shows ammonia engine research from University of Nottingham.
We've got. What I wanted to do for the last part of the presentation was actually show you some of the engine results that we've got. So whenever you have a new fuel, as an engineer, it's important to have a certain degree of skepticism over its operation and be realistic about it. And actually, we all had a healthy degree of skepticism around ammonia, but some of the results we've seen already are very encouraging in the engines that we've been running. So what you can see on the screen is a picture showing our thermodynamic single-cylinder engine. So you can think of this as being a typical automotive spark ignition engine. So this is typical of what you'd find in a modern passenger car fueled with gasoline, which is a very similar type of engine to a modern outboard engine on smaller boats and marine vessels. So state of the art, we've taken this engine and retrofitted cleaner fuels to the intake system, in effect. So what you can see on the left-hand side is a cartoon illustrating a slice through the engine's geometry. And the reason I've included it is it shows you how we introduce different fuels into this engine. So under normal circumstances, you can see the air gets breathed in the intake port, we call it the pipe, into the engine and tumbles into a bulk air motion there. We call it tumble, the circular motion of the air, and that makes the air very turbulent. And in most modern engines, we'll then directly inject gasoline fuel into the air, and that's what's shown by the orange arrow. So there's a direct fuel injector that's injecting E10. E10 is gasoline. It's gasoline with 10% ethanol in it, and that's what we use in the UK at the pump. So we've retrofitted ammonia to the engine's intake system. So the green arrow shows where we inject gaseous ammonia in with the incoming air. So that's one of the simpler ways for introducing ammonia engine. It's already in gaseous form. So what we have looked at in our initial experiments is we always start the engine using E10. We run it up to a fully warm condition, and then we co-fuel the engine. So we start to introduce some ammonia and we back out the amount of E10 until hopefully we're running on 100% ammonia. Keep in mind it's a very bad fuel in terms of being a very slow burning fuel. So our initial experiments focused on just one engine speed and load and trying this out. So that's shown in the table. So the speed was 1800 RPM, which is a typical reasonably high speed for something like a marine application or a stationary genset. And we operate the engine at about half load. So 12 bar net IMEP, so that's about halfway up the torque curve. And at each log, we always operate the engine stoichiometric. So in other words, as we add ammonia, we take out gasoline and keep the ideal mixture of fuel and air. And we always re-optimize the spark timing to give us the best efficiency at every point. And when we did that, you can see the engine out emissions shown on the screen. So the y-axis, if we look at the left-hand top graph, shows the CO2 in percent in the exhaust coming out of the engine. The x-axis is the amount of ammonia we were able to run. So 0 on the x-axis means we're running on 100% gasoline. 100 on the x-axis means we're running on pure ammonia. And what you can see is we weren't able, at this speed and load, to run on pure ammonia. Now, if we assume that that ammonia was made using renewables, electrolysis, the top 3 graphs show that we fully decarbonise the engine. So in the middle, the unburnt hydrocarbons go towards 0. There's no hydrocarbon in the fuel. On the right-hand side, the partially burnt carbon monoxide has gone towards 0. They're both slightly above 0. They're actually at the accuracy of our analyzer. So the only remaining small amount of hydrocarbon is due to the engine oil. And the bottom line is you can ignore it. It's next to nothing. So the punchline really is you can fully decarbonise an engine by decarbonising the fuel. So that's the first thing to know. The other thing to note in the bottom left-hand graph, this shows values of nitrous oxides. It should say NOx on the y-axis. It's all of the species. When people talk about ammonia engines, they often sometimes think they have a problem with NOx. In our case, we've halved the engine out NOx by just switching the fuel. The challenge is trying to understand the different species in those NOx. There's different forms of chemical species, and we're trying to understand those now at Nottingham, but it still looks encouraging. We've halved the engine out NOx just by changing the fuel. So that's the engine out emissions. It's a positive start. So the next thing that we looked at is
So next, let's talk about another field, natural gas. The availability of the domestic natural gas reserves, employing the filling infrastructure and state incentives help promote the increasing integration of the natural gas vehicle on transportation. Natural gas vehicles have increased in many captive heavy-duty frame applications, such as refuse trucks, transmission buses, school buses, and utility trucks. From this figure, we can know replacing a typical older in-use vehicle with a new natural gas vehicle predicted a significant reduction of the exhaust, such as the carbon monoxide, about 70 to 80%. No methanol organic gas, NMOG, by about from 50 to 75%. NOx by about from 75 to 95%, and carbon dioxide by about from 20 to 30%. This video shows us the natural gas engines work from main truck and buses. Yes, this video shows how dual fuel engine works from mine trucks and buses.
The MAN 3544DF. Its dual fuel technology with two separate injection systems makes it run on any fuel available, no matter if it's liquid fuel such as heavy fuel oil, marine diesel oil, anti-marine gas oil, or gas fuel like LNG. The 3544DF is based on MAN's well-proven 3244CR engine. Both engines feature a state-of-the-art common rail system with injection pressures of up to 1,600 bars. In diesel mode, this system and other technologies enable the 3544DF to fulfill the current emission regulation IMO Tier 2. To meet the even stricter emission limits of future regulation IMO Tier 3, the 3544DF can also operate in gas mode. Switching to gas can be done on the fly at loads between 15 and 100% with no loss in engine power. To ignite the air-gas mixture, a small amount of liquid fuel is injected by a separate pilot fuel system. In gas mode, the MAN 3544DF fully complies with IMO Tier 3, lowering CO2 emissions by 20% and other emission levels by up to 99% and beyond, compared to liquid fuel operation. The 3544DF features a fuel sharing mode. In this mode, both gas and diesel supply systems are active, which lets the engine run on multiple ratios of gas and liquid fuels. This makes the 3544DF virtually immune to variations in gas fuel quality, allowing it to operate even on gas that would be unusable for a conventional gas engine.
Okay. The last fuel is the methanol. Methanol is a recognized renewable clean energy. In the context of the carbon neutrality, it is of great significance to achieve no carbon production of the methanol fuel and its application internal combustion engine to reduce emissions. There are abundant sources of raw materials for the production of methanol, and the ecologic characteristics of methanol from all things and all things from methanol in nature. As a fuel, methanol has high economy, safety, environmental protection, reliability, and applicability, and is an ideal renewable fuel for traditional internal combustion engines. The engine used green methanol fuel can be carbon neutral, as shown in figure. CO2 is captured by various methods. Hydrogen is produced from renewable energy, and green methanol is synthesized from the captured CO2 and hydrogen produced from renewable energy. Methanol is combusted in the engine and passed through the exhaust aftertreatment device till it reaches CO2. And CO2 is captured and hydrogen native to form the methanol. Therefore, the combustion of the methanol in internal combustion engine can achieve a carbon-neutral cycle without increasing the CO2 emissions. Okay, the last part is conclusions. There will be 4 conclusions. Fourthly, the use of green ammonia in internal combustion engine is another variable route to carbon neutrality, with the advantage of not require a dedicated hydrogen supply infrastructure and the preparation, storage, and delivery of the liquid ammonia fuel for long-haul heavy trucks and marine power. Yes. Today we talk about low carbon and zero carbon fuel engines. That's all. Any question? Thank you for your attention. I hope you are having a wonderful day. Bye.